So far in this chapter, we've seen that a magnetic field can be created by a current carrying wire, and there's a force on a current carrying wire. So if we put those two equations together that we've already seen, and I'm not going to do the algebra to show you this to you, but what we end up with is that the two wires will affect each other. So in that situation we just looked at, where we have a current running in one direction from one wire and a current running in another direction from another wire, we actually get a force between the wires as they are together. So using our right-hand rule, the current in this right wire is going down. So I'm going to point my thumb down and then wrap my fingers around. And so we see that the magnetic field goes around this way, as shown in the picture. So here is my magnetic field. And then at the point where this other wire is, the magnetic field is into the screen. So we use our right hand again and point our fingers into the screen. The current is going up, and so the force is going to the left. So we use our right hand rule 2 times, once to figure out the direction of the magnetic field, and then once to figure out the direction of the force. This is the one place in physics where I know of that basically when we have two things that are the same, they're going to be attractive, and when we have two things that are opposite, they're actually going to be repulsive. And how does that work? Well, we just kind of explored the repulsive situation where we have current going in 2 different directions. So in this particular figure, basically we have to call one the source and one the reactive, but they're going to be mutually attractive or mutually repulsive. So if I take the wire, this time on the left, where we have the plus coming towards us, so we have the magnetic field coming towards the current coming towards us, so the magnetic field is wrapping around this way, right? So at the location of the other wire, the magnetic field is wrapping around this way. Right, we haven't morphed them yet. We haven't, considering that this one's creating a magnetic field. And then if I have the current going the other way, the magnetic field going up, the force is going to be to the right as well. So the force on this wire is this way. We'd end up with the force on this wire is away as well, because these magnetic fields aren't jiving. They're going in the same direction in that area, and so they're kind of trying to separate from each other. Whereas if we have the current going both in the same direction, so here again I have the current going into the screen, so my thumb is pointing into the screen. We have the current wrapping around this way. So if we do use our right hand rule, we'll find that the current wraps around this wire this way, and if this one's going in the same direction, it's wrapping around the same way. And so when we add up all the magnetic fields together, they end up looking like this shape. And then if we do our test, that in the location of this wire, the magnetic field is going down basically, the current is going into the screen, and so the force is going to be attractive. So here, 2 currents flowing in the same direction is an attractive force, and 2 currents flowing in opposite directions is going to be a repulsive force. And this is exact force is how we now define what an ampere is and what a coulomb is based on what forces we can generate from putting 2 wires next to each other. So basically it says if 2 long parallel wires are 1 meter apart carrying the same current and the magnitude per force is this number, then the current is defined as being 1 amp. And then similarly for 1 coulomb. Watch a short video and he's actually going to demonstrate this principle.
For part 3, we're going to look at 2 parallel wires. And for the first one, we're going to look at the current running in the same direction. So current comes out of this wire, goes into both, comes down and goes into ground. So they're both going down. And we're going to hit this button. And we're going to notice they're brought together. And then we're going to flip them around, so it's going to go up this first one, through, and then down the second one. We're going to hit this button, send current, and you notice they spread apart.
So I hope that was nice to actually see this happen, that the forces between the wire is a thing, and that like current in the same direction is attractive versus current that is opposite direction is actually the repulsive version. So in this situation, we want to levitate a wire above another. So our sum of forces is we want to always have gravity pointing down. And we're going to use weight per length because this is newtons per meter is given as a weight per length. And so that's down, because always down. And then we have our force derived magnet over length that we're going to have as the upward force, so the force that's counteracting gravity. So formally what I'm doing is the sum of forces in the y direction is 0. So that means FB over L needs to equal to my weight over length. And so that number is going to be at 0.073 newtons per meter. And then I'm going to use my formula here to figure out what the magnitude of that force is and ultimately solve for D, because that's how far is what we're trying to solve for in this problem. So solving that for D gives me D is equal to mu naught I1 I2 all over 2 pi times F over L. And we can put the numbers in to get that. And so those are the numbers we get, only 6 millimeters. And whenever I put these in the calculator, I just cancel out the pi's, and here we cancel out the 2's. So I would type this in as 2e negative 7 is the fastest way to type that in the calculator. It makes the fewest amount of mistakes. But what we want to do also is verify that the forces are going the direction that we think they are. So we get the magnetic field from the lower wire. And so we point our finger in the direction of the current, our thumb in the direction of the current, and our fingers wrap around in the direction of the magnetic field. So in the top area, as the figure shows, the magnetic field is coming straight out towards us. And these are lines tangent to those circles. And then the current on the top is going the other direction. So we take out our right hand again to figure out what the force is doing. So the magnetic field is coming out this way, so it's kind of hard to do. It's pointing towards you. And then the current is going that way. So I have my basically palm straight up. The magnetic field is towards behind me. The current is to the left, and so the force is up. So that is how we said it was going to be, is that the force is up on this wire. So the force is up, the magnetic field is out, and the current is to the left. Now is your chance to answer the question is, if we have a loop of wire, is this thing, if we have wire that's not sturdy, is it going to collapse or is it going to try to expand? So think about that for a minute. What's going to happen, collapse or expand? So hopefully you got a chance to think about it, but we have two sets of parallel wires, and the current is running in opposite directions. So what's going to happen is that for the top and bottom, for the bottom wire, again, my current is going this way, so the magnetic field is wrapping around this way. So this force is going to be out, and likewise, that force is going to be out. So all the forces are going to be out, meaning that basically away from the center of the loop. So that they're trying to get away from each other. The loop is going to tend to expand if it can.